Hi, this is Dr. G. Welcome to our statistics review. This is a video that will cover some of the basics of statistics. Let's start with a few definitions. First, population. What is a population? Well, it's the entire collection of units of analysis or observations or elements upon which information is desired. It's just a large collection of individuals or objects known to have similar characteristics. So what are these objects, these elements? I referred to them a moment ago as units of analysis. Well, these are the units upon which measurements are taken. So populations are comprised of these elements or these units of analysis. Let's think of an example. How about the population of all college students or all graduate students? What are the units of analysis in this case? The unit of analysis, or the unit upon which measurements are taken, in this case, is students. So students comprise the population, and we're referring to all college students. We're interested in studying properties of some numerical characteristic of the population of units of analysis. So what's the characteristic that we might be interested in studying for all college students? Maybe grade point averages. So that's an example of a population, all grad students or all college students. The units of analysis are students, and the numerical characteristic that we're interested in studying in this case is grade point averages. So once we've identified a population of numerical values of interest, we take a sample. So there are different reasons why we take a sample. A couple of big ones. Number one is cost. In other words, it's a heck of a lot less expensive for me to take a random sample of all graduate students and measure some numeric characteristic like grade point average versus measuring that numeric characteristic for the entire population. So cost. And then the second reason is that it's possible to use sample information to obtain really good information that we can use to make inferences about the population. Basically, what I'm trying to say is sample information is high impact information. So if we take a random sample, or if the sample is truly representative of the population, I can measure some of the numeric characteristics of those samples and make inferences about the entire population. So I might be able to randomly sample 100 students versus the millions of students in the population, and I might be able to say something about those millions of students with my random sample. So that's the beauty of statistics and working with samples. Low cost, number one, and number two, high impact information. So once we get our sample, we often take an estimate of the following parameters. First, the mean. Next, the range. We can arrange grade point averages in ascending order to see what the lowest value is, to see what the highest value is. We can look at how grade point averages are distributed. So for example, we might expect to see a normal distribution for this particular variable. And we can measure the dispersion of the data looking at variance and standard deviation. We'll talk about all of these quantities in more detail in just a bit, but my point right now is simple. Instead of working with entire populations, we work with samples, and we can use samples to obtain measurements of important statistical quantities. Sometimes we look at the median and the mode and other measures of central tendency in addition to the mean. So for example, if the data is highly skewed or if kurtosis is high, we might prefer to look at the median instead of the average or the mean. And we can supplement that data with other numerical properties, for example, the interquartile range, the variance, and the standard deviation, just the ones that we've already mentioned. All right, so before we explore these concepts in a little bit more detail, I'm going to go ahead and go to my Stata Actually, I'll go to the program that I'm going to run. I've got a projects folder under my C drive. So I've got a projects folder saved on my C drive. So if I click on my C drive and go to projects, there is a statistics review folder. And the program that I'm going to work from is stat review. There's also stats review. They're basically the same, but I'm going to work with stat review to recreate the stats review program. And this is what it looks like. So this isn't really a lesson on programming, but we often use statistical processing software packages to perform data analyses because it saves time. It can do some really fast, powerful things in programs versus using Microsoft Excel or worse, versus doing it by hand. So that's going to be something that we're going to do, even though it's not necessarily required for you to learn. So just pay attention to the basic statistical concepts, and I think you'll be in really good shape. But reproduce these programs to get some practice in Stata if you're working in Stata. And of course, you can also use Microsoft Excel. If you're taking one of my classes, then I'm probably asking you to reproduce these programs in Stata for credit. Okay, so I always start programs with the following lines of code. The version line, capture log close, set log type text. That's to create a text file for logs. I create a log or a log file with this command, log using stat review, comma replace. If you want to learn more about a particular command, just type in help and then the name of that command. And this is the log file, or the help file for the log command. That's actually a little large, so I'll go to 12. So under the title, you'll see the manual that contains this particular command. You'll see the syntax, and you'll see all of the different ways that you can use this command. We're using log using the name of the file. The name of our log file is stat review, not stats review, it's stat review, because I'm working in my stat review.do file that I created. You can create a new do file just by clicking on this tab and writing away, or just going to File and Open. And you can start a new do file. It's really easy. So log using stat rev, the suffix for this file is a .log file, and then I'm inputting the replace option so that when I run this program more than once, it doesn't stop on an error, hey, that file already exists. I'm going to replace that file every time that I run the program. So I can highlight the commands that I want to run, press this arrow, and if I go to view stat rev.log, I can see the log file. Of course, there's nothing in it because we haven't really done anything. Next, I set more off that so that Stata doesn't stop when the results window, which is here, is full. This is the results window. When it's full, Stata will stop. So I use this command set more off so that Stata flows smoothly through all of the results. This is a command to change directories. That just says go to a different folder, and the folder that I want my computer to work from is on the C drive under the projects folder, and it's the stats review folder. So if I run that, and if I type in directory into the command prompt, we can enter commands here. I can see all of the files that are in this folder. And again, if you're taking one of my data analytics oriented classes, you probably have a folder that contains all of these files. I'm going to import some data, but first let me just re-emphasize the point that I'm going to make. There are times when we use the median instead of the mean to learn more about the data under analysis. When do we do this? We do this when the data are highly skewed. So let me import this data. This is data that contains economic statistic information, income information. So if I click on Browse, you'll be able to see the data that we're working with. And we have real incomes for these different years, 1975, 1985, 1995, and 2005. And we've got tons of observations. We've got 100,000 data points. So for each one of these years, we took a random sample from the population, 100,000. I can obtain summary statistics for these variables by typing summarize. To do this in Excel would take forever. You'd have to highlight one column, input equals average if you want the average, and then highlight that data. Input equals STDEV for a sample, highlight. But in Stata, if I type in this command, it gives all of this information to me instantly. And if I want even more information, I can input summarize and then detail. And for every one of the variables, it'll give me lots of details in addition to the summary statistics. So you can tell by looking at the data that the skewness and kurtosis values for income, 1975, it's high. We'll talk about skewness later, but as you can see, these values are pretty high. We can visually inspect the data by looking at a histogram. So I'm going to put histogram. And again, this is just a graphical representation of the distribution of data. And I'm just going to pick one of these years and press go. Too many variables. Okay, that was an error. And as you can see by looking at this histogram, and you can create these types of tables in Excel too. Again, it takes forever and a day. But we've got a big hunk of information and then data that tails off to the right. In other words, it's very, very skewed. So let's look at 1975. The 85 data is so skewed, it's almost hard to even see. But here you can see that we have a right skewed distribution. When variables are normally distributed, they look like this. So we might look at income, or we'll put stock prices. I'll put stock prices. And this is the distribution. They might look normally distributed. But we just saw that income is very right skewed. It kind of looks like that, right skewed. The vertical axis is the density function. I'll just put f of x, or this is the f of stock prices, where stock prices are our independent variable. And if I want to get the probability of obtaining a particular stock price, I just go from the horizontal axis to the density function, out to the vertical axis, and then I'll get my likelihood or probability using the density function. There's actually a formula for f of x for normal distributions. That density function formula varies by distribution. Most of the variables that we're going to be looking at are normally distributed. We're going to be looking at sample statistics, which are almost nearly always normally distributed because of the central limit theorem and how sampling distributions work. We'll talk about that later. But again, this distribution just tells me, this would be the average stock price, how the data are dispersed around this average. And again, that sort of information can be very meaningful. Let's say we have two distributions. Let's say we've got stock A versus stock B, and this is the distribution of A. Of course, this is not drawn to scale. And let's say the expected return, or the average return for A, is equal to 15%. And let's say stock B has an expected return also equal to 15%. But let's say the data are distributed like this. In other words, they don't really spread out around the mean too much. So the range for stock B might be 12 to 18%, whereas the range for stock A might be negative 50 to, I don't know, 115% or something like that. So the point that I'm making is, if I know the measure of dispersion and the expected return, I can learn more about the data than just the expected return alone. So if I know standard deviation or variance in addition to the average, I can use that information to achieve a better understanding of the variable under analysis. Okay, so back to the example. We want to use the mean when the data are highly skewed. When the data are highly skewed, we should not use the mean. So if I go back to Stata, and if I look at the summarized information, the average is 38,000 a year to 40 to 40 to 48,000 a year. If you look at per capita income now, the average is probably about $57,000 per year. But if we lined up the entire population from the poorest to the wealthiest and looked at the 50th percentile, we would be able to see the income for which half of the people in the country make less and half of the people in the country make more. So let's solve for the median. I think we did this already, but you just input summarize in detail. And the median is the 50th percentile. So as you can see, in 1975, it's about $25,000, and this is inflation-adjusted data changed to a particular year, so it takes into consideration changes in the cost of living. And from 75 to 85, it's the same, 25,619. 1995, about 24,000, and then again back to 25 in 2005. So basically, what we're saying is that for the middle-income, middle-class individuals, the median has stayed about the same, even though the average has increased over time. And we know that that distribution of this particular variable is very right skewed, and that's because of people like Mark Zuckerberg, Bill Gates, and heck, maybe some of you guys. So now we know why we look at measures of spread, the standard deviation, in addition to the averages. So stock A versus stock B. I want the spread in addition to the expected returns or the average returns, because if I know that the expected returns between the two stocks is the same, I'm going to invest in the one with the lower standard deviation. I'll be able to plan better. I get more bang for my buck. I take less risk per unit of return if I invest in stock B. So we know that looking at measures of dispersion are very important, and we can easily obtain these measures of dispersion from Microsoft Excel or Stata. Here's the measure of standard deviation for each one of these variables. And again, this data is highly skewed. If I go to the program and I import this data from a statistics module, I'm going to get Microsoft returns, daily Microsoft returns from an old stats module. So I'm running the program. Stata is still thinking. It's only because this data is pretty big that now I've got new data. So I can press browse like I did before, and now I've got one variable, daily returns for Microsoft stock. And this data is going to be much more normally distributed. I'll look at the histogram of the returns, and as you can tell, the average is about 0, which is not uncommon for daily returns. And the variability goes from about -1 or -0.1 or -10% to 10%. And we're normally distributed around 0 in this range. So again, we like to look at averages. If the data are skewed, we'll look at means and other measures of central tendency, maybe the mode. And we need to supplement our mean data and mode data with measures of dispersion like standard deviation and variance. I can summarize the Microsoft daily return data. I can also use codebook. It's another command besides summary that gives me more information. So as you can see, I get the percentiles. I still get the average and standard deviation, but I get the range that we were referring to earlier. I can see whether or not any data is missing. I can see the number of unique values. And it looks like there are 5,000 observations in this particular data set. So all of that information is given. And again, I can construct the histogram. So let me go back to the stats review folder. I'm going to grab some more data. I'm going to run this program through grabbing this data, and I'll show you the log file before we start to hit our stats review a little bit harder. So view is another command, stat review.log. So this is the data that contains a log of every result that Stata produces. And again, we save these log files so that we can reproduce results. The Stata results window will fill up. When it fills up, the program will continue to run because we've set more off. And all of those results, once the Stata results window is full, all of those results past that won't be accessible. So we have to look at our logs. Or we can just run segments of our program by highlighting those lines of code and then pressing the execute option, which is this little file with a blue arrow on the bottom right. All right, so let's do a couple more definitions before moving on to some of the basics of probability. And we've mentioned these concepts very briefly, but let's be a little bit more specific. What is statistical inference? When you think of statistical inference, just think of learning something or using a few things to learn about all things. So the few things, that's the sample, all things, the population. So in statistical inference, it's basically the science of using sample data to make generalizations about an entire population, but this only matters if our sample is representative. So we want random samples. So each unit of analysis or each observation or each element needs to have the same probability of being selected. If that's the case, we've got a truly random sample. It's representative of the population, and because of that, we can do statistical inferential procedures. In other words, we can look at that sample and we can infer from it things about the population. Next, statistical estimation. So what is statistical estimation? When you think of statistical estimation, think of the science of using information contained in a sample to, one, find some sort of a statistical estimate of an unknown population parameter, and two, to place a bound on how far that estimate might deviate from an unknown population parameter. So again, the science of using information contained in a sample to find an estimate of an unknown population parameter and to place a bound on how far the estimate might deviate from an unknown population parameter. So essentially what we're going to do is use our sample information to find estimates for things like averages, maybe a slope coefficient in a regression model or an intercept coefficient. We're going to use the sample to solve for a statistic. And then we're going to use statistical ideas like the central limit theorem to be able to say something about how far that estimate deviates from the true population value. Again, we'll cross that bridge when we get there. But in statistical estimation, we're using the sample to estimate statistics. We look at how those statistics are distributed, just like we look at how variables are distributed. And then we use information from our sample and our understanding of how sampling distributions work to learn more about the population through statistical inference. Okay, moving right along to the next topic, probability. And this is something that you guys have probably learned at some point in the past, but I'm going to give you guys a little baby review because we're going to be working with lots of probabilities. We won't be working with probability theory so much, but we'll be using discrete distributions and continuous distributions of variables to solve for probabilities. We'll be using tables in the back of the book, normalized variables to make probability statements. You'll see that it's really, really easy, but before we do that, we have to review probability. Again, it'll only take a few minutes, and then we'll move right into more sophisticated statistics. All right, the concept of probability is employed in describing populations and in using sample information to make statistical inferences. So let's review a few terms. First, experiment. So what is an experiment? We can define an experiment as any process of observation that has an uncertain outcome. So a process with an uncertain outcome. So any process of observation that has an uncertain outcome. An example would be drawing a card from a deck of cards or flipping a coin. So the flipping of the coin is the experiment. The rolling of the die is the experiment. If I ask you to pick a number 1 to 100, that's an experiment. It's a process and the outcome is uncertain. Next, what is an event? An event is simply an experimental outcome that may or may not take place. So it's an experimental outcome that may or may not take place. That may or may not take place. Again, an experimental outcome, an event is an experimental outcome that may or may not take place. Next, what is a probability? It is a number that measures the chance that the event will occur when the experiment is performed. So it's the chance that the event will occur. So the chance that the event will occur when the experiment is performed. So a probability is just a chance, the number between 0 and 1. For all practical purposes, the probability of an event is simply the proportion of time the event would occur if the experiment were performed a large number of times. So for example, the experiment of flipping a coin, what's the proportion of time that heads will occur if I perform that experiment, the experiment of flipping a coin 100 times or 1,000 times? Obviously that proportion is about 50%. So that's all a probability is. So if A is an event that may or may not occur when the experiment is performed, so an event that may or may not occur when an experiment is performed, then the probability that the event A will occur is denoted as PA. So this is notation that you'll see in stats or quant-oriented courses. So PA, if A is an event that may or may not occur when an experiment is performed, then the probability that the event A will occur is denoted PA. So PA is just the probability that the event A will occur. So if the experiment is performed, say, NEXP times, And the event A occurs NA times, so we might perform the experiment of flipping a coin 100 times. And let's say the event of heads occurs 50 times, then NA divided by the number of times that we perform the experiment is equal to the probability of heads. In this case, it would be 0.50 or 50%. If the number of times that we repeat the experiment approaches infinity, the limit of the sequence of numbers obtained by calculating the ratio n sub a divided by n sub exp after each repetition is the probability of a, the probability of that event occurring. So mathematically what we're saying is that the probability of A is equal to the limit as the number of experimental trials approaches infinity, NA divided by N EXP. So again, this is, a more technical definition of a probability. So the question is, or a little example, what is the probability of heads, or the probability of that event, for the experiment of flipping a coin an infinite number of times? So as we let the number of trials in the experiment increase to infinity, or as n sub exp increases to infinity, we flip that coin over and over and over. As we approach infinity, the ratio of n sub a to the number of trials, n sub exp, will equal 0.5. But again, I want to go back to the definition of a probability that you should sort of reference. When you think about a probability, just think of simply the proportion of time some event occurs if some experiment is performed a very large number of times. And we know that the probability has to be less than 1 but greater than 0. And we'll spend a lot of time working with probabilities in this class. We won't be working with probability theory so much, which is probably something that you discussed in your introductory statistics class while you were an undergraduate student. But we'll use continuous probability distributions to make probability statements. So let's say this is the distribution of some variable, some random variable. So if we know how this variable is distributed, and in this case it's a normal distribution, and if we normalize the variable so that the mean is equal to 0, so that we're looking at standard deviations from the mean, and again, this will all make more sense later. But if I ask a question, what is the probability of observing a value greater than 0? So what is the probability of observing a value greater than 0? Well, we know that the area under the curve is 100%, and in this case, that probability would be 0.5. We might inquire about the probability of observing a value of this variable that is in between -1 and +1 standard deviations from the mean. And again, we just solve for the area under the curve. We can do that using tables, or we can do that using Excel or statistical processing software like Stata, and easily obtain those probabilities. Okay, so moving on to random samples and sample statistics, we know that the calculation of population parameters, for example, solving for the population mean, requires knowledge of all the values in the population. If we don't know all the values, we must obtain a sample of n values from the population. So let's say the population has 1 million individuals. Let's say we're talking about college students or graduate students in Masters of Science programs If that population contains 1,000,000 students, we might select a random sample of 1,000 students. So a random sample of n elements, in this case 1,000 students, can be obtained if each student or each element has the same probability or chance of being selected in the sample. If we randomly select a sample of n elements, or students in this case, the values of the numerical characteristic of interest, we were talking about grade point averages from before, so the values of the grade point averages possessed by these students make up a randomly selected sample of n values. So for I from 1 to 2 to n, we let y sub I denote the value of the numerical characteristic under study possessed by the ith randomly selected element. So the set of y1, y2, all the way through yn. And we sometimes think of y as the dependent variable. Don't. In this case, y is just some variable. In our example, y is grade point averages. So if we have a sample of 1,000 GPAs, we'd have GPA 1, GPA 2, all the way through GPA 1,000. And that is our set of data. So this is our randomly selected sample of 1,000 students. The set of G1 to G1000 is the randomly selected sample of 1,000 numerical values. So what is a sample statistic? Moving right along, what is a sample statistic? So what is a sample statistic? A sample statistic, it's just a descriptive measure of a randomly selected sample of numerical values, some sort of descriptive measure. We could use sample statistics as point estimates, or estimates that are single numerical values of population parameters. So if the population under analysis contains 1,000,000 students, I generate a random sample of 1,000 students. We can use this sample to solve for sample statistics. It's just a descriptive measure of the randomly selected sample of numerical values. So what sort of descriptive measure? Well, we can solve for the mean, we can solve for the variance, we can solve for the standard deviation. There are all sorts of sample statistics that we can solve for. And again, we use these random samples to solve for sample statistics. And we use these sample statistics as point estimates, or estimates that are single numerical values of population parameters. So although I don't know the population grade point average, I can take a random sample from the population and solve for the sample. So suppose that the sample is y1, y2, all the way through y sub n, and this is a randomly selected sample from a population. How do we solve for the average grade point average, or the average y? Well, in this case, we would just take the values of the individual elements from I is equal to 1 to n, and it's the number of students. We would take each student's grade point average and just divide that by n. So that's just the sample mean. How about the variance? The sample variance is often denoted S squared. It's a measure of variability. It's simply the sum of the squared deviations. So I is equal 1 to n y sub I minus y bar squared, all divided by n minus 1. In the numerator, we have the numbers of degrees of freedom. And since we're using this sample to solve for the mean, we have one less piece of information. So the number of degrees of freedom is reduced by 1. So the total number in the sample less 1. So if I look at a set of data and if I know what the mean is, then I don't need one of the y values. I can solve for the last y value with all of the other y values and the mean if I know what the sample size is. Anyways, just know that the degrees of freedom, when you work with a sample, you don't divide by n. You don't take the average of the sum of the square deviations. You take something close to the average of the sum of the square deviations. You divide by n minus 1. This is a point estimate of the true variance. The mean is a point estimate of the true mean. And if I take the square root of the variance, I get the standard deviation, which is an estimate of the population standard deviation, often denoted as sigma. We can solve for all of these values using Excel. I'm tempted to give you some numbers and ask you to solve for the mean, the variance, and the standard deviation, but I'm trusting that you can do that. If you haven't performed those calculations in a while, well, actually, we can just do like a weird baby example. Let's say we've got 3 values, so n is equal to 3. What is the mean? This might be some characteristic that we're interested in studying, but this is a random variable. There are 3 values. The values are 2, 4, and 6. So how do we solve for the mean? So y bar would be the sum I is equal to 1 to 3. Y sub I, and then all of that divided by 3. So 2 plus 4 plus 6 divided by 3, which is equal to 4. So y bar is equal to 4. Well, what about the variance? So the variance is the sum of the square deviations divided by n minus 1. So I'll do this just maybe once or twice, but I'm not going to spend a lot of time doing this sort of math. We can solve for these things very easily by hand. I know that this is way too fundamental, but we've got I is equal to 1 to n s sub I minus, y sub I minus y bar squared, all divided by n minus 1. So that's going to equal, well, the average is 4, so y bar is 4, so y sub 1 is 2. So 2 minus 4 squared plus, so you just perform this mathematical process, take a difference and square it for each I, for each student, or for each observation. So 4 minus 4 squared plus 6 minus 4 squared, and we divide that by n minus 1, or 3 minus 1, which is 2. So negative 2 squared is 4, plus 0 plus 4 is 8, divided by 2, which is equal to 4. So that is the variance, and I can take the square root of the variance to get the standard deviation. So in this case, the standard deviation is 2. So this is the cool thing. If you know the variance, or if you know the standard deviation, and if you know the true population average, and if you know the standard deviation, you can normalize these values and make all sorts of probabilistic statements if we know how this variable is distributed. So we'll get to that in a little bit, but those are just some baby examples of how you perform those calculations by hand. So let's move on to continuous probability distributions. So continuous probability distributions. So continuous probability distributions, and I know I'm going fast, and I can give you notes packets to supplement this discussion, and you're probably following along. So before we randomly select a value y from a population, y potentially can be any of the values in the population. So let's say that we've got 1 million students, and I randomly select 1 student and get their grade point average. That grade point average can be something between 0 and 4. It can be one of the population values. So we can use continuous probability distributions to calculate probabilities concerning y, the value that y might attain. So again, we can use continuous probability distributions to calculate probabilities concerning the value y might obtain. So again, if I'm just randomly selecting somebody from the population, y potentially can be any of the values in the population. So I can use the continuous probability distribution to calculate probabilities concerning the value y might obtain. This sort of implies that I know the probability distribution, so we'll see some examples in just a minute. But for now, consider the closed interval from A to B on the real number line. So we're going to denote this interval as follows, A to B. We often wish to find the probability that y will be in the interval A to B. We often wish to solve for this particular probability, and we can write this more simply as the probability that y is less than or equal to B, but greater than or equal to A. This probability can be interpreted as the proportion of values in the population that are greater than or equal to A and less than or equal to B. So continuous probability distributions assign probabilities to intervals of numbers on the real number line. So if I know how a variable is distributed, I can use a continuous probability distribution to obtain the probability of observing a value greater than A, but less than B. So again, continuous probability distributions assign probabilities to intervals of numbers on the real number line. So let's suppose that f of v is a continuous function of numbers on the real number line. So when I say function, it's just a formula. And for different distributions, we're often given this function. But suppose that f of v is a continuous function of numbers on the real number line. Consider the continuous curve that results when we graph this function. So let's say if we graph this function, we get something that looks kind of like this. As you can see, this variable is normally distributed. We can say that the curve f of v, so this curve is the continuous probability distribution of y, that the probability that y will be in the interval A to B is the area under the curve f of v corresponding to the interval A to B. So let's say that A is some value of the independent variable and B is another value. And this is a standardized metric of y, but I can look at the distribution of y or some standardized measure of y, call that v, and look at the continuous probability distribution, f of v, and I can use this continuous probability distribution of y if the probability that y will be in that interval A to B is the area under the curve, f of v, corresponding to this interval, so this area here. So the example that's in the notes is we've got a continuous probability curve f of v, and let's say that it represents the continuous probability distribution of the mileage of a randomly selected automobile. So we've got the continuous probability distribution of y. In this case, y is the mileage. The variable is the mileage of a randomly selected automobile. And suppose we wish to find the probability that y will be between 31 and 33 miles per gallon. So this might be 31 and this is 33. We can standardize these values, 31 and 33, using statistical processes that we'll cover in just a minute. And if we have some more information regarding how this variable is distributed, we can easily solve for the area under the curve in between A and B, or the probability of getting a mileage in between 31 and 33 inclusive. So if the curve f of v is the continuous probability distribution of y, then we say that the population of values from which y will be randomly selected is distributed according to the continuous probability curve f of v. So in other words, the population has the continuous probability distribution defined by f of v, and this height, the height of the curve. So if I look at the probability distribution of a variable, so if I look at the probability distribution of this variable v, and it could be mileages, there's some standardized mileages, and I know its distribution, and if I pick some value randomly, I'll just say v1, if I go up to the curve and then out to the vertical axis, I get the f of v1. So the height of this curve at any given point on the real line, which is the horizontal axis, represents the probability. It's really a relative probability that the value, that y, will be in a small interval of numbers around this point, v sub 1. So in other words, if this variable is mileages, and if I pick some value of mileages, I can solve for the relative probability by working off of this function that will be given. Of course, we can solve for these things automatically. It's very easy, especially these days using technology, but I just want you guys to know that there's a formula. F of v is a formula, so if I give you values of v, I can run them through this formula to give you the probability, the relative probability of observing a particular value of v. And I can use formulas to solve for not only the relative probability of observing a particular value of v, but the probability of observing a value that falls in the interval a to b. So I can get probabilities by looking at the area under the curve in between 2 points. So I can say, hey, listen, if you invest in this stock, there's a 47% chance you'll earn between 10 and 15%. Or I can say something like this: the relative probability that you'll earn 10% is equal to 0.001. If that makes sense. And again, this is a relative probability. You know that if v is continuously distributed, so it's measured on the real number line as a continuous variable, so it can be infinitely divided. The probability of any particular value is 0, so these are relative probabilities, but we can think of them as just probabilities. All right, so two properties satisfied by the continuous probability distribution are: 1, for any number v, f of v is going to be greater than or equal to 0. So basically what we're saying is that the probability is in between 0 and 1. Remember, the height of the curve represents a relative probability. And we can think of it just like some sort of a probability. And these probabilities have to be between 0 and 1. And then also the continuous area, or the total area under the continuous probability distribution. So the total area, this cross-hatched region, but the total area under a continuous probability curve is equal to 1. And this holds because the total area under f of v, this function, equals the probability that y will be between negative infinity and positive infinity. So I've got negative infinity here, and then positive infinity here. Actually, let me write those as negative infinity to positive infinity. So again, if we standardize the value of the variable under analysis, and if it's infinitely divisible, we've got an infinite number of values that v can take. And if we take the sum of all of these different values under the curve by solving for the area under the curve in between negative infinity and positive infinity, we get 1. I know that sounds a little too statistical, but this is stuff that you've probably seen before. To spend some time looking at the notes packets And again, if you have any questions, feel free to call me anytime. But when we start to do examples, you'll see how easy this is. This is all a little bit too theoretical now, but when we start to work with specific probability distributions, like the normal probability distributions, we see formulas for the density functions, and we see how we can solve for the relative probabilities of particular values and the cumulative probabilities of intervals. Things will start to make more sense. All right, so moving right along to the normal probability distribution. So we're going to discuss the normal probability distribution. This is also known as the bell curve. This is something that you've already read about. This is something that you've definitely seen working on your bachelor's degrees. So it's a normal probability distribution. Many of the variables that we study in business are normally distributed. We saw an example earlier when we looked at the daily returns from investing in Microsoft stock. We saw that they were normally distributed about 0. So the normal distribution is very, very common in business. Not only that, not only are many variables normally distributed, but sample statistics are normally distributed. So even if a variable isn't normally distributed, if I solve for the average of that variable and then solve for another average using another sample, and from the population take sample after sample after sample and solve for average after average after average, if I look at the distribution of those averages, they will tend to a normal distribution. Anyways, the normal distribution is the continuous probability distribution that is defined by the following probability curve. F of v is equal to 1 divided by sigma, the standard deviation, multiplied by 2 pi, all multiplied by the natural logarithmic base raised to the exponent of negative v, which is the value for any particular value, or which is the value of the variable minus the average squared divided by 2 sigma squared. So all of this is the exponent. So e raised to the exponent of the negative of the value of a particular value of the variable minus the average, the true population average squared divided by 2 sigma squared. And this is for all values of v less than infinity but greater than negative infinity. So basically what I'm saying is, for any normally distributed variable, if I know what v is, I can pick a value for that variable. I can solve for the relative probability using this function. Of course, computers solve for these things automatically, and I'll show you guys how to do that in a moment. But before we were talking about grade point averages, this would be the true population grade point average. Sigma squared and sigma, these are the true measures of spread. If I know one, I know the other. But these are the true or population measures of spread. So these things are given. If I know sigma and if I know mu, the true measure of spread and the true average, well, of course, I know E, 2.71828 or something like that, and pi 3.14. I know everything besides V. V is a particular value of the variable under analysis, the normally distributed variable. I can solve for the relative probability by using this function for all values of V from negative infinity to positive infinity. If I graph this, it will look like this. So that is the normal probability distribution. So if a population is distributed according to a normal distribution, we say that that variable is normally distributed with mean mu and standard deviation sigma. The normal probability distribution is denoted by n, mu, and sigma. And this basically means that the shape of this curve depends on two things: the mean and the standard deviation. So here are two examples of normal curves. And let's give them the same mean, but different standard deviation. So that mean might be 10. But one is much more spread out than the other. And we might have a couple of normal distributions that have different means. So that might be 10, and let's say this is 20. So different means, but about the same standard deviation. Of course, that's not drawn to scale. But the point is this: we define the curve, or the shape of the curve is defined by the mean and the standard deviation. Okay, some important properties of the normal curve. It's centered on the mean, mu. The mean corresponds to the highest point on the curve. So the highest point is the mean, and we can solve for that relative probability using our normal probability distribution, probability density function. Also, the normal curve is symmetrical around the mean. In other words, 50% of the curve is above the mean and 50% of the curve is below the mean. And then finally, the total area under the curve from negative infinity to positive infinity is 1. So the population mean centers the normal curve on the real number line, and the variance measures the spread of the normal curve. So if a variable y is normally distributed with mean mu and standard deviation sigma, then the probability that y is greater than or equal to a but less than or equal to b equals the area under the normal curve with mean mu and standard deviation sigma corresponding to that interval a to b. In other words, a might be a little bit to the left of the mean and b might be a little bit farther to the right. And I can solve for the probability that a particular value of the random variable, I might say that y is normally distributed. I might standardize y and solve for v's that map to the y's. We'll talk about that later. But basically what I'm saying is that if the variable is normally distributed, and if I know what the mean and the standard deviation, or I can solve for the area in between a and b, and that's the probability that y is greater than or equal to a but less than or equal to b. So here are three important areas under the normal probability distribution. So I'm going to draw a normal curve, trying to draw this to scale, but not even close. So remember, the normal distribution is centered on the mean, and there are 1, 2, 3 standard deviations to the right. There are actually more than -3 and +3 standard deviations to the right and to the left of the mean. But the probability of observing a value of the variable more than 3 standard deviations from the mean is very low. And we can learn how to solve for those here in a minute. But popular areas under the curve are three important areas: the area in between -1 and +1 standard deviations at 68.26 6%. So I solve for this area. If I know what the standard deviation is, and if I know what the average is, or if I standardize the variables, in which case the mean is 0, and if I standardize the values of the variables, if I look at the area under the curve in between -1 and +1, then I will get exactly 68.26%. Well, how about the area in between -2 and +2 standard deviations? That area is approximately 95%, 95.44%. And the vast majority of the area under the normal distribution is between -3 and +3 standard deviation, so 99.73% of the area under the curve is in between -3 and +3 standard deviations from the mean. So that is 6 standard deviations, or 6 sigmas. So if you wonder where the term 6 sigma comes from, it comes from the normal distribution. All right, so let's use the frequency option. So if you look at the syntax for this command, we type in histogram, the name of the variable. We can use an optional if qualifier, an optional in qualifier, and we've got continuous and discrete options, and then options that apply in both cases. So when you see something in brackets, these are optional components of the syntax, and then everything after the comma, which is optional, is comprised of options. And then here we've got continuous options or discrete options, and then general options. So one of the options is the frequency. So we can look at the histogram, and we can see the frequencies instead of the densities. And this is what it looks like. So on the horizontal axis, we see 1, 2, 3, 4, 5, 6, 7 bins. And each bin is a range of the values of the variable mileage. And we can see the frequency. We've got 49 observations, and we can see the frequency on the vertical axis. So in the histogram, the frequency of values of a variable within an interval is measured on the vertical axis. The total number of intervals or bins is on the horizontal axis, and we can use the frequency distribution to sort of see the chances of occurrence of a particular value of a variable and how the chances change from one bin to the next. And this can be more easily accomplished by looking at the relative frequency distribution. So you can see that that is an option. That's the density when we want the density on the vertical axis. So if I want to see the density, I can see that there is about a 30% chance I'm going to get a value that is in this bin range, about the same probability in this bin range, over 50% in the top bin range. So basically what it is, it's very similar to the continuous probability distributions that we studied earlier. We can use them to make probability statements. When we were looking at the normal curve, we talked about how we could use it to make probability statements. Well, you can do the same with the frequency distributions and the relative frequency distributions, which look at densities instead of frequencies. Basically, what I can do is look at this to make probability statements. So again, the relative frequency or density for a bin is simply the number, it's simply the frequency of the occurrences of values within that interval divided by the sample size. So again, if I find that there are 14 occurrences of values within a particular interval or bin, and if I've got 100 observations, then I can say, okay, the probability that I'm going to see randomly select a value that is in the range of whatever that bin width is, I know that that probability is 14%. Also, the number of intervals or bins chosen should be the smallest. Here, actually, we'll do this in smooth draw, but the number of bins chosen should be the smallest integer k, such that 2 raised to the exponent of k is greater than n. So I'm going to say this again, and we'll just sort of scratch out the example that we're working with by hand so that we can really interpret what a frequency distribution is. But the number of intervals or bins, so the number of bins or intervals on the horizontal axis, the number of basically bars chosen should be the smallest integer k, such that 2 raised to the exponent of k is greater than, and well, here n is the total number of observations. So this is the trick. You can just set 2k equal to n, and then just round up to the nearest integer. So it's the smallest integer k, such that 2k is greater than n. So you can just set 2k equal to n, and then round up to get that smallest integer k such that 2k is greater than n. Hopefully that makes some sense. It sounds like kind of an SAT problem or something like that, but it's really not that bad. All right, so in our case, what does n equal? I think we had 49 observations. So in our example, n is equal to 49. So how do we determine the number of bends? We just take the number of total observations, set that equal to 2k, and then round up. So how do I solve for k in this case? Well, you have to know properties of logarithms. Again, Stata determines the number of bins automatically, and that'll usually be given. But if I take the logarithm of both sides, it's k log 2 is equal to the natural log of 49. And then I can divide both sides by the natural log of 2. And I get k is equal to log 49. K is equal to log 49 divided by log 2, or I take the natural log of 49 and I divide that to the natural log of 2, divide that by the natural log of 2, and I get 5.61. So that is equal to 5.61, and then what do? We round up to 6. So that's the number of bins that we should use, but we don't have to use that number. We can use a little bit more or a little bit less. What about the interval widths? So the next question has to do with interval widths. So again, with the frequency distribution, we're just taking a variable, mileages, and we're sorting it from smallest to largest. And then we're taking that range of values and we're creating bins. And then we look at our data and we see how many observations fall in each bin, what the frequency is. And then we can take those observations in a particular bin and divide that by the total sample size to get the density. So we can look at the frequency or the density. If you don't like density, just think of the relative frequency. So it's really simple. So let's talk about the interval width. So this is pretty straightforward. Once we solve for the number of class intervals, here we solve for 6, we can get the bin length. Basically what we do is we divide the range of the data by the number of class intervals. So we take the range, the smallest from the largest value, and divide by 6, or the number of intervals. Well, how do we find that range? Remember, I can just do some mileage, and I can see what the range is, 29.8 to 33.3. So we take that range, 33.3 minus 29.8, supposed to be an 8, and we divide that by 6, and I get 0.58, just round up to 0.6. We're getting 0.6, that's our bin width, and we get 6 intervals. So the class width is the distance between the lower limits of consecutive classes. So now we've got the class width, and that's just the distance between the lower limits of consecutive classes. So we'll see that there are 6 classes. The distance between the lower limits is the class width. Once we have the class width, you can create the first interval by adding 0.6 to the smallest value of the variable, the smallest mileage. In this case, it is 29.8. So let's see what this looks like. So the interval would be 29.8, but less than 29.8 plus 0.6, which is 30.4. Not less than or equal to, so I denote that range of data instead of using brackets. So less than or equal to, or the base of the range to the top of the range inclusive. We're going to do the base of the range to the top of the range not inclusive, so not including 30.4. So basically what I'm saying is 29.8 but less than 30.4 is the first width. So that's that first bar. 29.8 but less than 30.4. So 30.4 is the next bottom of the class width. So 30.4 but less than, so I add 0.6 to 30.4 and I get 31. And then 31 but less than 31.6, I'm not writing it all out. And then 31.6 but less than 32.2. And 32.2 but less than 32.8. And then finally the last interval is 30, that looks like a weird 3, 32.8 but less than 33.3. So these are the bin widths, and I can see what the frequency is. So I'm going to draw the frequencies. I'll just point little arrows for these two, and then I'll draw the rest to the right. And then this is beautifully written in the notes, so hopefully you have those out in front of you. But in the first bin, we've got 3. In the second bin, we've got 9. Then we have 12, 13. We have 9 in this bin. And then in the 6th bin, we have 3. So we've got 6 bins. 1, 2, 3, 4, 5, 6. And then 1, we've got 3. And then 9. And then we've got 12. And then 13, 9 again, and 3. So hopefully this sort of looks like what we're getting in Stata. We know the intervals. So what is the probability that I get a value in between, or a value greater than 31, greater than or equal to 31, but less than 31.6? What is the probability? Well, it's 12. 12 is the frequency, but the probability is 12 divided by the total number of observations in our data. So 12 divided by the total number of observations in our data, we're working with 49 observations, and that gives us about 24.45%. So the probability that I see that I randomly select a value from my data in between 31 and 31.6 non-inclusive is about 24%-ish. I'll just put about 24%. So again, if we look at the histogram in Stata, hopefully it will look something like this. So let's do the histogram again, and There you go. And if we do the histogram frequency, we've got 7 intervals here, so it's not exactly. So we can tell Stata to do 6 intervals. We can tell Stata to do 6 bins instead of 7, and then you'll see that it looks very similar. But you get the drift. Why do we do this? So that we can make probability statements to help us understand the chances of the data that we see. So if I look at a particular variable and I look at a value for that variable, is that value rare? So if I'm looking at IQ, I know the average is 100. What if I see a value equal to 147 or something like that? Well, if the standard deviation is 15, I know that seeing a value equal to 147 is extremely rare. If I see a value equal to 60, I know that that's extremely rare. So again, we can use histograms and stem and leaf diagrams to make probability statements regarding our data. And again, this just gives us more information in addition to just the average. We're looking at measures of spread. We're following a pretty standard approach. This is usually typically one of the first things that you'll do in most statistics classes is just talk about histograms and how you can graphically display information and use that to make probability statements before moving deeper into inferential analyses where we work with probability distributions, just like we're working with histograms to make probability statements. We're going to be working with continuous probability distributions to make probability statements. Okay, moving right along, let's talk about the standard normal distribution. So for every value of the independent variable, there is a standardized value for that variable. So for every y value, there is a z value. Let's just do a quick example, and then I'll follow the notes a little bit more specifically. All right. Let's say that we're dealing with IQ. Sorry, when I draw on my Wacom bamboo tablet, it's making a funny noise that doesn't sound like art. Anyways, sounds like something that rhymes with art. Anyways, so here is my normal distribution. Let's say that we're going to talk about IQ. And I know that the true average of IQ is equal to 100. I know that the average IQ is equal to 100, and I also know that the standard deviation is equal to 15. And I know that there are 3 standard deviations to the right and to the left of the normal distribution. I'm going to redraw this normal distribution so that it is just a little bit easier to use. That's just too tiny. Okay. So I know that IQ is normally distributed, and I'm just going to make this bigger. So this is the distribution of the variable IQ. And I know that the average is equal to 100. I know that the standard deviation is 15. So if I go 1 standard deviation to the right, I get 115. If I go 2 standard deviations to the right, that would be about 130, 145, and then lower and lower probabilities for values greater than 145. To the left, 100 minus 15 would be 85. 85 minus 15 would be 70, and then 70 minus 15 would be 55. And then if I go to the left of that, I get lower and lower likely values. So if I tell you what the mean is, and if I tell you what the standard deviation is for a particular variable, I can make probability statements. I know that under the curve, there is about 68% in between -1 and +1 standard deviation. It's about 68%. I know that, so I can say if I randomly select somebody from the population, there's about a 70% chance that their IQ is going to be between 85 and 115. So I can make those types of probability statements. Well, what is the probability of getting something in between 74 and 132? See, we don't know that. So what we do is for any variable, we can standardize it. You can standardize a variable by subtracting out the mean. So let's say I've got IQ for a particular individual. I can subtract out the mean of IQ, and then I can divide that by the standard deviation, the true standard deviation of IQ, and this allows me to obtain a Z value. This allows me to obtain a Z-value or a standardized value. So long story short, why would we standardize a variable by subtracting out the mean and dividing by the standard deviation? It's because Z-values are the same for all variables. If I say, hey, listen, I'm looking at mileage as data, and let's say the average miles per gallon is 32 miles per gallon, and I'm looking at a car that gets 37 miles per gallon. What's the probability of that happening? Or what's the probability of seeing 36 to 42 miles per gallon versus 22 to 28 miles per gallon? To be able to make those probability statements, it's kind of hard. What you need is a table. So if you standardize any variable and you look at those standardized values, you can say things like, you know what? If I see this value, it's 3 standard deviations to the mean, or 3 standard deviations to the right of the mean or to the left of the mean. It's pretty rare. But that makes sense if I speak in terms of standard deviations or Z-values. You can tell when you normalize a value, essentially what you're doing when you subtract out the mean and you divide by the standard deviation is you're looking at how many standard deviations a particular value of the variable is from the mean. Take that full distance and divide that by standard deviation, you get 5, and that means that that particular IQ is 5 standard deviations from the mean. So we do this for one reason. We solve for Z values so that we can easily obtain probabilities. The probabilities associated with observing a particular value of a normally distributed variable or a particular range of values of a normally distributed random variable. So let's just normalize these variables very quickly, and then we'll see how we can make those probability statements using z-tables in more detail. But again, the only reason we normalize is so that we can make probability statements, so that we can make confidence interval statements. It's just to make everything easier. So for the value of 55, let's solve for the z. Well, 55 is the IQ minus the average, which is 100, divided by 15 is equal to, well, if you do the math, it's -3. What about 115? Well, 115 minus 100 is 15, divided by 15 is 1. So that's 1, this would be 2, this would be 3, this would be -1, this would be -2, and 100 minus 100 divided by 15 is 0. So we've mapped IQs to Z's, and now that we have Z's, I can use the Z-table to make probabilistic statements. The Z-table is standardized, and it gives me the ability to make probability statements. Well, what is the chance of seeing an IQ in between 92 and 147 or something like that? Or the area under the curve in between these 2 points. So we'll be able to do that here in just a couple of minutes. But the reason why we standardize variables, you know, we can solve for these probability values if we don't standardize the variable. We just need a table for every variable. So IQ is measured on a different scale than miles per gallon, which is measured on a different scale than Walmart profits, which is measured on a different scale than your level of anxiety or your level of happiness or some sort of a psychological construct or psychological variable. So the fact is, we normalize values of variables so that we can use one table, the z-table, instead of a million tables for a million different variables to make probability statements. So again, for every y value, there's a z value. Thus, there's a population of z values that we can map to, or that corresponds to the population of y values. So if y is randomly selected from a normally distributed population with mean mu and standard deviation sigma, the z-value corresponding to the y-value can be solved for using a formula just like this. What we would do is just take the y-value that we observe. It's normally distributed. It's randomly selected. So it's randomly selected from a normally distributed population. We know that the mean is mu, and we know that the standard deviation is sigma. And this just tells me the number of standard deviations. This is a distance measure, and it gives me the number of standard deviations. The number of standard deviations y is from mean mu. So the standard normal distribution, if y is normally distributed with mean mu and standard deviation sigma, so the true population mean and the true population standard deviation, if y is normally distributed with mean mu and standard deviation sigma, then z is normally distributed with mean what? With mean 0 and standard deviation 1. So when we normalize the variable, the mean is scaled to 0 and the standard deviation is scaled to 1. So the standard deviation is scaled to 1. So if we subtract mu from the inequality, just bear with me for a moment, let's say that y is less than or equal to b, but greater than or equal to a. So let's subtract mu from this inequality, and let's divide by sigma. So if we subtract mu and we divide by sigma from this inequality, we're just going to do that to all of the values in the inequality. So a minus mu divided by sigma, so we're basically just solving for z values, is less than or equal to y minus mu divided by sigma, which is less than or equal to b minus mu divided by sigma. Remember, this is just, a to b, so we're mapping these a, b values to standardized z values. So essentially what we're saying is that z would be less than or equal to the z value that corresponds to the b value, which will be greater than or equal to the z value that corresponds to the a value. Hopefully that makes sense, but basically what we're saying is that instead of looking at this interval 85 to 115, we know that 100 is greater than or we know that values in this range are greater than or equal to 85 but less than or equal to 115. Well, we can map that to -1 to +1. So essentially what we're doing is just saying what we said before, and z sub a is the z value corresponding to point A. So there's a z value that corresponds to point A, and then z sub b is just the z value that corresponds to point B. So we know that the probability of observing a y value less than or equal to b but greater than or equal to a, we know that that probability is exactly equal to the probability of observing a z value less than or equal to z sub b, which is greater than or equal to z sub a. When we start to put numbers to these inequalities and probability statements, I think it'll make a little bit more sense. But again, this is just a stats review. Essentially what I'm doing is reviewing a lot of weeks of statistics in a relatively short tutorial. So feel free to ask questions if you have them. You can send me over an email or you can call anytime. All right, moving right along. All right, so let's do an example. So the question is, and this is in the notes, if the population of all mileages is normally distributed with mean mu equal to 31.5 and standard deviation equal to 0.8, what is the probability that will observe a value less than or equal to 33.1 but greater than or equal to 29.9, So 29.9. So what is the probability that we'll get a value greater than or equal to 29.9 but less than or equal to 33.1? So how do you do this? You solve for the z value corresponding to 29.9 and you solve for the z value corresponding to 33.1. And with this information, you would use the z table to solve for the probability of getting a value greater than or equal to 29.9 or less than or equal to 33.3. So let's solve for the z values first, and then I'll show you guys how to do this in Stata. So we're going to solve for the z values, and then we're going to plug and chug and put them in the z table. So I'm just using a calculator. You can't see it, but well, I guess I should probably do it so that you can see it. All right, so 29.9 minus the true mean. Remember, we subtract out the mean and then divide by the standard deviation. So 29.9 minus 31.5. That gives me negative 1.6, and then we divide that by the standard deviation, and we get negative 2. 33.1 minus 31.5 is 1.6, and we divide that by the standard deviation, and we get 2. So we get a z value. So now we want to know the probability that we get a z less than or equal to 2, but greater than or equal to negative 2. So let's look at the z table, and then I'll show you guys how to do this in Stata. This is a z table. It gives you the z value associated with the area under the curve in between 0 and that z value. So we know that the z values are negative 2 and 2. Okay, here's the table. So we know that the z values are negative 2 and 2. So I go to z equal to 2.0. And I know that in between 0 and z, a z of 2, 0.4772 is the area. Now I also know that this curve is symmetrical. So the area in between 0 and negative 2 is also 0.4772. So the total area in between negative 2 and 2 is 0.4772 times 2. So that would be 0.4772 plus 0.4772, and voila, 95.44% is the answer. So the probability that I get a value in between 29.9 and 33.1 is 95.44%. Let's do this in Stata. So before we hop into Stata, remember we saw a really fancy formula for the density function. We saw a fancy formula for the f of z value, and we said that that gives us the probability, if this is z, that gives us the probability of the relative probability of a particular z value. And right now we're learning how to solve for these areas in between values. So we're able to get these relative probabilities and these probabilities. Well, there are Stata functions that make this possible, that make it possible to solve for these things automatically. So I'm going to type in display normal 2, and that gives me 0.9772498. That's the area under the normal curve in between negative infinity and 2. But I want the area in between negative 2 and 2. So I want the area under the normal curve in between negative 2 and 2. So I can put display normal 2 minus normal negative 2. And I get that same answer, 0.954. 0.44. Check it out. Display normal 0. Now remember, the average, the standardized, once we normalize or standardize a variable, its average is 0. So what is the area in between negative infinity and the mean? It's 50%. So I can solve for the cumulative area in between negative infinity and some value by using the display normal command. I can solve for the relative probability by using the display normal density command. This is the trick. In Stata, you have to first standardize your variable. You have to normalize. You have to subtract out the mean and divide by the standard deviation. Now, once you do that, and you get those z values, which correspond to which map to the values of the variable under analysis. So if we pick a variable, grade point averages, for every GPA, there's a z-score. So if we take a sample from a population, or if we're just looking at the population, I can get a z-score for every GPA. Once I get those z-scores, I can solve for the relative probability of a particular value. So let's say the average GPA is 2.5. We normalize it, and now that average maps to a normalized value equal to 0. What is the relative probability of getting that value? Well, it's 39.89%. What is the probability of seeing a variable that is 5 times larger than or 5 standard deviations past the mean? So display normal den 5, well, it's negative 0.00001487. So you just move that decimal 6 places over. That gives you 5 zeros before the 1. Basically 0. Display normal density. Let's say we're just going 2 standard deviations. 5%. So we can solve for the density values and the cumulative values by using the normal function, or the normal density function, and the normal function in Stata. It's that easy. All right, to perform calculations in some statistical inference procedures, we need to sometimes find the z-value such that the area to its right under the standard normal curve. So we need to find the z-value such that the area to the right of the area to its right under the standard normal curve is gamma, or z associated with that area to the right. We sometimes call this a critical z value, and we compare the critical value to calculated z values to perform hypothesis tests. So again, this is just the z value associated with some area to the right. This area might be 0.025. So what z value corresponds to an area of 2.5% under the standard normal distribution? That's z sub gamma, or the critical z value. We'll revisit that later, or actually let's just do a quick example. Find the critical z value that gives us 0.025 area to the right under the standard normal distribution. So let me open up my z table. Okay, so here's the z table, and remember, this gives us the z value associated with the cumulative probability in between 0 and that value. So if we want 0.025% in the tail, that gives us a cumulative probability of 0.5 minus 0.025. So I want the z value that goes from 0 all the way up to 0.4750. In other words, what is the z for which 2.5% of the area under the standard normal distribution is to the right of that value? Well, if I look at this table, I can see that 0.5 minus 0.4750 is 2.5% or 0.025, and that is associated with a z-value equal to 1.96. So from 0 to 1.96 is the cumulative area of 0.4750. Well, I know 0.5 is in between 0 and infinity. So 0.5 minus the area up to the z-value associated with 1.96, 0.5 minus that area, 0.4750, gives me that area left in the tail. So again, this is a symmetrical curve. I know that in between z and infinity is 0.5. Well, I know that the z-value that gives me 0.4725% in between 0 and 1.96, the z-value in between 0 and I meant to say the cumulative area under the curve in between 0 and 1.96 is 0.4725. So 0.5 minus 0.4725 gives us the, 0.4750. So 0.5 minus 0.4750 gives us the 2.5%. I'm not sure what happened there, but let me fix that. That should be 0.4750. So 0.5, which is this full area, 0.5 minus the 0.4750, which is this area, the pink area. So 0.5 minus the pink area gives us the, let's say, this area right here, that 2.5%. And again, this will make more sense when we do statistical inference later. All right, make sure to read through the notes to learn about the F distribution, the chi-squared distribution. These are other distributions. Lots of statistics follow the F distribution and the chi-squared distribution. Again, we can use these distributions to make probability statements. So if I know a particular statistic has an F distribution, then I can use that information to make probability statements. If I know a particular distribution has a t distribution, which is basically like the standard normal distribution, we'll talk more about the t distribution here in a bit, but it's basically like the standard normal distribution. And if I know a statistic follows a t distribution, I can use that information to make probability statements. And if I know a statistic follows the chi-squared distribution, I can use that information, again, to make probability statements. So review those distributions in the notes packets. I've included links. I don't have time to go through every distribution, but again, it's in the notes. You're getting a really good review now. But let's move on to confidence intervals for a population mean. So confidence intervals for a population mean. That's the next topic. So confidence intervals for a population mean, and we're going to actually work with confidence intervals a lot. This is something that you'll do in between now and the time you stop doing research. So confidence intervals are very important. So we can use the sample mean, y bar. So this is just a variable, and we solve for the sample mean. And again, we're talking about populations, but we're going to build up to that. We're going to first refer to a sample, but we can use the sample mean and the sample standard deviation, which is denoted by S. We know how to solve for these. That's just the sum from the first value to the last value divided by the number of values. That's the mean. And the standard deviation is the square root of the variance, which is just the sum of the squared deviations, or the average of the sum of the squared deviations. We have to divide by n minus 1, so it's not an exact average. We have to take into consideration the fact that we lose a degree of freedom in solving for the mean before we solve for the standard deviation. Anyways, we can use the sample mean and the sample standard deviation to solve for an interval estimate of the population mean. So we can use this information to solve for a confidence interval. So why would we do this? Well, the mean by itself doesn't give us any indication of how close it is to the population mean. And that's the information that the confidence interval provides. So a 100 multiplied by 1 minus alpha percent, and I'll talk about what alpha is in a minute, but a 100 multiplied by 1 minus alpha percent confidence interval for the population mean mu based on the t distribution, a small sample. In other words, the t distribution is just like the normal distribution. If you look at the normal distribution, it'll look something like this. The t distribution takes on the same shape, but the tails are a little bit fatter. So it's a little bit less precise relative to the normal distribution. We use the t distribution when we work with small samples. We'll talk about that in a minute. But the 100 multiplied by 1 minus alpha percent confidence interval for the population mean mu based on the t distribution can be solved for as follows. We take the sample statistic and we add and subtract the critical t value, and we'll talk about this in a minute. This alpha is popping up a couple of times. We'll talk about it in a minute. That's t raised to the x, that's not t raised to the x, no, that's t. This is t sub alpha divided by 2 supra n minus 1 denotes the critical t value with the alpha divided by 2 area in each tail under the t distribution with n minus 1 degrees of freedom. And then we multiply that by the standard deviation divided by the square root of the sample size. That's the square root of n. Let me write that more clearly. N. So this is just, and when we do this, you'll see how easy it is. We take the critical t value multiplied by the standard error of the mean of the sample standard deviation divided by the square root of the sample size. So that's the base of the interval, 2y plus the critical t multiplied by s divided by root n. So we're just taking some amount. You can tell that it is this amount. We're taking some amount and we're subtracting it from the mean and we're adding it to the mean to get the confidence interval. And remember, t sub gamma supra degrees of freedom, which is n minus 1, that is the critical t value. So basically what we do is we solve for the critical t value and we solve for the sample standard deviation. We can get that. We know n, so we can get the square root of that. We get this, the critical t value, from the table. We can solve for the sample mean. So all of this information we can easily obtain to create this interval. Alpha is the level of statistical significance. It's the significance level. We get to pick it. And if we want to be 95% confident, we'll say alpha is equal to 5%, which means that we're taking alpha divided by 2 and we're putting 2.5% in each tail under the t-distribution, and we're going to find this range, this 95% confidence interval range, and we're going to be able to make statements like, I'm 95% sure that the true population mean is in between this bottom number, and this top number. So that's pretty amazing when you think about it. We're going to use sample information, and we're going to be able to say something like, I'm 95% sure that the true value is contained within that interval. It's pretty cool. That's what we call inferential statistics, using a sample to make those types of inferential statements. All right, so I'm going to read through example 3, and then we can do that in Stata. So it says, federal gasoline standards state that mu, the mean gasoline mileage obtained by the fleet of all some vehicle, in this case Hawks, must be at least 30 miles per gallon. So those are the federal gasoline standards. You've heard about the CAFE standards. To demonstrate that this standard is being met, National Motors randomly selects a sample of 5 cars and tests them for gasoline mileage. And in the sample, these are the values that we get. So remember, we're working with a set of data Y1 all the way through Y5, and these values are 30.7, 31.8, 30.2, 32.0, 31.3. So these are the values. We've taken a random sample of 5 Hawks, and we want to solve for the 95% confidence interval for the true population mean. So let's do this in Stata, and we can confirm some of these values by hand, but the fact of the matter is we do this using computers. So I'm going to clear the data in memory. So if I type in list, I don't get anything, and I'm going to run this portion of the program. It just says input this variable. These are the values of that variable, end. So this is like a baby program within a program. And now when I list, I've got my 5 miles per gallon, and I can estimate that confidence interval by using the command a means, miles per gallon. And that's that. I know, how easy. Oh, very quickly, we won't do 100% of this program, but there's a portion of this program that I've included just to give you a feel for how important programming is. But for what we'll do, we're nearly done. But back to the confidence interval, let's see. The arithmetic mean, there's also the geometric and harmonic provided. The geometric mean, you've probably heard of that before. You've probably studied it in finance classes, but we'll just look at the, Y bar. And the 95% confidence interval is 30.27 to 32.13. So we're 95% sure that the true population value is somewhere in between 30.27 approximately and 32.13. So in this example, we picked a level of confidence equal to 95%. We picked a level of confidence equal to 95%. So let's solve for this by hand, just so that it's clear that it's easy to do. So the only thing that we need is the critical t-value. The only thing we really need to find is the critical t-value. So first, we need to get the critical t-value. And we're just going to do this by hand very quickly. We won't do a lot of this stuff by hand because it just takes too long. But we've got this t-table. And again, since it's a t-table, the tails are a little bit fatter than the standard normal distribution. So I'm letting more space exist between the horizontal axis and the density function. This is the density function. And we're looking at the variable miles per gallon, but we'll just put f of t. because we're normalizing that. So what is the critical t-value that leaves 2.5%? Let me write that more clearly. That leaves 2.5% under the curve to the right of the t-value. So what's that critical t-value? Well, here's a t-table, and I know that the number of degrees of freedom is equal to 5, which is the number of observations, n minus 1. So 5 minus 1 is 4. 4 is the degrees of freedom. The upper tail probability is 0.025, so I go over to 0.025, and I see that that critical t-value is 2.776. So this critical t-value is 2.776. Let's just solve for the top portion of the interval. Let's just solve for this portion here. Going back to Stata, I can summarize miles per gallon, and I see the average is 31.2, and I see the standard deviation is 0.751663, so 0.7516643. I can just copy it, and I can ask to display that value divided by the square root of 5. So you can do that in Stata, but I've already got it going here in a calculator. So anyways, I'm just going to divide this by the square root of 5 because I have it here, and I get 0.33615. So I know the critical t-value is 2.776. So when I multiply the critical t-value by the standard deviation divided by the square root of the number of observations, the standard deviation divided by the square root of the number of observations is called the standard error of the mean. We'll talk about that in a little bit. And then I multiply that by the critical t-value to get that 0.93316. And then I add that value to the mean of 31.2. So plus 31.2, and voila, 32.133. And that's what we got here, 32.133. There's some rounding error, but that's how we get the top of the interval. We would take this value, 0.93316, we would subtract that from the mean to get the bottom of the interval. So 31.2 minus 0.93316, and we get 30.266. And again, I didn't take that all the way through, so there's some rounding error, but you get the point. It's that easy. Moving right along, let's talk about how we derive this interval. And I won't get into all of the details in the notes. Again, the details are in the notes, but I'll give you guys some pointers. First, let's talk about a sampling distribution. We can get a sampling distribution by taking repeated samples of a population. So suppose we take a sample, we solve for the mean, and then we take another sample from the population and we solve for the mean. And then we do that over and over and over and over. So for any variable, I can take a sample and I can solve for the mean. I can sample and sample and sample. Let's say for college grade point averages, I take 1,000 samples. And for each sample, I solve for the mean. And then I look at how those means are distributed. In other words, I can look at how the means are distributed. So instead of looking at the distribution of grade point average, I'm looking at the distribution of the average, grade point average. The distribution of grade point averages might go from 0 to 4, but the distribution of the average will be tighter. But this is the cool thing. When it comes to sampling distributions, or looking at the distributions of statistics, so we're not looking at the distribution of the individual grade point averages. I can look at the entire population of grade point averages and I'll solve for the standard deviation and it'll be high. But if I solve for the standard error of the population mean, or the standard deviation of the sample statistic, the mean, that measure of dispersion will be lower than the measure of dispersion for the individual values, which is interesting. So essentially what I'm saying is, not only can I look at how the individual values of a variable are distributed, but I can look at how the values of a statistic are distributed. I just have to sample over and over and over again. For each sample, solve for the statistic, in this case the mean, and then look at those means, look at how they're distributed. That's called a sampling distribution. And again, an important result is that the mean of a sampling distribution is equal to the population mean. In other words, the mean of the sampling distribution will be equal to the population mean. So you can take some more advanced statistics classes and actually prove that to yourself. You can prove it by hand or prove it through simulations, but it's really neat. It's a neat result. And the sampling distribution of the mean, so if we take sample after sample after sample and solve for those means and we look at the distribution, they will be normally distributed, even if the individual values of the variable are not normally distributed. So even if the population values are not normally distributed, the distribution of the statistic, the mean, will be normally distributed. Very quickly, the population of all possible sample means has, well, to get this 100 minus, to get the 95% confidence interval, we have to review some pretty important results. We already know how to solve for the interval, but just very quickly, if we look at the sampling distribution, the average of the averages, so if I take the average of the sample means, I will get the true population mean. The sampling distribution has a variance equal to sigma squared divided by n. So the variance of the sampling distribution, or the variance of the distribution of sample means, is sigma squared divided by n. So we have a standard deviation of the sample means equal to sigma divided by root n. And again, the population of the sample means, or I'm sorry, the sampling distribution has a normal distribution. So the average of the sample means will equal the true population average. The variance of the sample means equals the true population variance divided by n. So if I take the square root of that, the standard deviation of the population means, this is also called the standard error of the mean, is equal to sigma divided by root n. That's kind of familiar. And the distribution of the means, so the distribution of the y bars, is normal. So you can tackle example 4 when you get a chance, but it states that if the true values of mu, sigma squared, and sigma are 31.5, 0.64, and 0.8, so let's say mu is equal to 31.5. Let's say that sigma squared is equal to 0.64, and let's say sigma is equal to 0.8. The question is, what are the values for the average of the averages, the variance of the averages, the variance of the sample statistic, and then the standard deviation of the sample statistic? So given this information, what are those values? And again, you can solve for them on your own. We know that the average of the average equals the true population average, so that's 31.5. And we know that sigma divided by root n is equal to the standard error of the mean. So 0.8 divided by, we said n equals 5 from before, so 0.8 divided by 5, 0.8 divided by, not 5, the square root of 5, and that gives us 0.358. So that's the answer to that question, and that question is in the notes. So if we assume that the population of all mileages is normally distributed, if this is the case, then the population of all possible sample means is also normally distributed. Even if the population of all mileage is not normally distributed, the population of all possible sample means is likely normally distributed. That's the result, the statistical result that comes out of the central limit theorem. So let's say we want to know what the 95.44% confidence interval is. Well, we know about the standard normal distribution. We know that that mean of means plus or minus 2 standard deviations, those are the standard deviations of the means, or the standard errors, that is going to equal 31.5 plus or minus 2, we've already solved for this, 2 multiplied by, what was it, 0.358, and then this gives us an interval 30.784 to about 32.216. So what does that mean? Well, we know that under a standard normal distribution, we're not working with the t, we're working with the z value now, in between -2 and +2 standard deviations. Remember, we did that already. In between -2 and +2 standard deviations, we get 95.44% under the curve. So 95, the result is this. The area between -2 and +2 is 95.44% under the curve. I could look at a z-table to find this information out. I just used Stata. So what's the result? Thus, 95.44% of all possible sample means lie in the interval 30.784 to 32.216. So 95% of all possible sample means lie in that interval. So basically what we're saying is that if the population that is sampled is normally distributed, then the population of all possible values of the sample mean minus the average of the averages of the true sample mean divided by the standard error is equal to y bar minus mu divided by sigma divided by root n. So again, if the population that is sampled is normally distributed, then the population of all possible values of this has a standard normal distribution. Basically what we're saying is that our sample statistic, the sample mean, which is y bar, the sample mean, we can normalize it. We can subtract out the true mean and divide by the standard deviation, and we'll see that it is also distributed normally. Now, if I look at the distribution of the means, it's going to be tighter than the distribution of the individual values. So again, in the context of grade point average, if I look at the distribution of all GPAs of all students, it's going to be a wider distribution than if I look at the distribution of the means. So the means will sort of average out the really high GPAs and the really low GPAs. It'll take this very dispersed measure of individual values and tighten them up a bit. But the point is this sample statistic is centered on the true value, and I can use that result to make probability statements that make it possible to infer information about the population from the sample. So let's say we are not working with the true population standard deviation. Let's say that we have to estimate that with a sample standard deviation. It can be proved that if the population that is sampled is normally distributed, the population of all possible values of y bar minus mu divided by s sub y bar, which is just y bar minus mu divided by s divided by root n, has a t distribution. So when we know the population standard deviation, we've got a normal distribution. When we don't know the population standard deviation, we've got a t distribution. But this statistic, again, this is just like a z value, but it's called a t value. This is a t value. So for each mean, I can map it to a t value, and those t values are, you guessed it, t distributed. They follow a t distribution, which is kind of like a normal distribution. Instead of having tails that nearly touch the mean, the t distribution has tails that are a little bit farther away from the mean. So again, if the population is normally distributed, the population of all possible values of the t value, the standardized or the normalized population means using the sample standard deviation, that's going to be t distributed with n minus 1 degrees of freedom. So this sort of implies that, oh good, I'll be able to fit it here. This implies that the probability, let me write that over, the probability of getting a t value, so y bar minus mu divided by s divided by root n, the probability of getting a t value less than or equal to this critical value associated with a particular alpha level and degrees of freedom, which is greater than or equal to this t value, the negative t value associated with that alpha and degrees of freedom. So basically what I'm saying is that I can find this t value, the negative t value, that puts alpha divided by 2 area in the tail with n minus 1 degrees of freedom, and this positive t value, that's an alpha, well, I'll write it over, alpha divided by 2 with n minus 1 degrees of freedom. So if I put, let's say, 2.5% in each tail, 2.5%, and I find those critical t values, then I've got a 95% interval. So if I find these critical t values by putting 2.5% in each tail of the t distribution, I can say that some randomly chosen value of the mean lies within that interval 95% of the time. So again, this is a probability equal to 95%. So the probability that this value is greater than or less than the critical t on the lower end and less than or equal to the critical t on the upper end, this probability is equal to 95%. So what I can do is manipulate this result to derive the confidence interval. So again, these are t values, and the math, I think, is broken down in the notes in more detail. And of course, we're never going to have to derive these intervals. We're just going to be told how to solve for them. But if we wanted to, we could. So we know that the probability that this value is greater than or equal to the lower t and less than or equal to the upper t is 95%, what we can do, so that is equal to 1 minus the alpha level, and we choose that. If we choose a 5% alpha level, essentially what we're saying is that we're going to be 95% confident. 95% confident. So the probability that a particular t value is greater than the lower critical value but less than the upper critical value is 95%. So I can multiply this inequality by this quantity. So I'm multiplying that by that quantity, and then I'm multiplying that by that quantity. And then what I can do is add or subtract the mean from both sides, and then multiply everything by -1 to obtain the confidence interval. So again, if you multiply both sides by s divided by root n, and then you subtract out the mean from both sides, and then you multiply everything through by -1, and remember when you do that, the inequalities switch, but this is the result that you get, and it's the result that we saw from before. But long story short, the confidence interval is solved for as y bar plus or minus the critical t given a particular level of confidence and degrees of freedom, and we're going to do some examples in just a second, all multiplied by s divided by root n. And that gives us the confidence interval for mu. So I can write this a little bit differently. Let me see if it'll fit. So I can put mu, we can manipulate this equation to show that mu is going to be less than or equal to y bar plus the critical t, which is alpha over 2. The critical t depends on the degrees of freedom and the level of significance, times s divided by root n. So the true value is going to be less than or equal to y bar, the sample value, plus that quantity, the critical t, times the standard error, but it's going to be greater than or equal to y bar minus the critical t, degrees of freedom, multiplied by s divided by root n. So this is equal to 95%. So what we're saying is that the true value, the true mean, lies within this interval, y minus the critical multiplied by the standard error, so y minus the critical multiplied by the standard error, to y plus the critical t value multiplied by the standard. The true value lies in this interval 95% of the time. So we can say something about how close our sample statistic is to the true value given some critical t value that depends on the degrees of freedom and the level of alpha. So again, just going through the notes, it says that the proportion of confidence intervals containing the population mean mu in the population of all possible 95% confidence intervals for mu is equal to 1 minus alpha, or 0.95. So basically 95%, the proportion, 95% of all confidence intervals that we estimate will contain the population value mu, which is neat. So once we estimate a confidence interval, we can say that 95% of the time that interval will contain the true value. That's a little bit different than saying that the proportion of confidence intervals containing the true value in the population of all possible 95% confidence intervals for the true value is equal to 95%. But that's sort of like, those are logic statements. For all practical purposes, when we solve the confidence interval, 95% of the time the true mean is going to be in that confidence interval. So we've got that neat result, y bar plus or minus the critical value multiplied by the standard error. So that means that 95% of the confidence intervals and the population of all possible 95% confidence intervals for the true value mu contain mu. And 95% of the confidence intervals in this population, and 5% of the confidence intervals in this population do not contain mu. But the main thing is 95% of the confidence intervals in the population of all possible 95% confidence intervals for mu contain mu. That's the big result. So let's move on to confidence intervals based on the normal distribution. And I think that in between, from here on, it'll go by pretty fast. So as you know, this example is based on the t distribution, and it assumes that the population sampled is normal. The t distribution, we're working with a small sample, but we can now consider a confidence interval that is valid for any population. The math is pretty much the same with a couple of slight differences. But the central limit theorem, and we've talked about it already, basically says that if the sample size is large, and when we say large, basically what we mean is, larger than 30, then the population of all possible sample means is approximately normal, with the average of the sampled, the average of the averages equal to the true population average. So if I take the sampling distribution of the mean, or if I take the average of all of the sampled means, that's going to equal the true average, and the standard deviation is going to equal sigma divided by root n. So that's the standard deviation of the sampling distribution, or the standard error of the mean. So basically what the central limit theorem is saying is that if n is big, we can use the z's instead of the t's, that the mean follows, that the average of the average is equal to the true mean. It's unbiased, basically, and that the standard deviation is equal to sigma divided by root n. So if n is large, the population of all values of this quantity, y bar minus the true divided by the standard deviation, has a standard normal distribution. So this basically means that y plus or minus the critical z, and again, this all depends on our chosen level of significance, so that's alpha divided by 2, divided by the standard error of the mean. So this implies that these quantities, y bar plus or minus z, alpha divided by 2, and then suppose we're working with the sample standard deviation instead of the population standard deviation, that both of these quantities are 95% confidence intervals for mu. So both are 95% confidence intervals for mu, and this is when we have a sample size greater than 30. Again, we can derive these intervals using a similar process as before, but that's not necessary. You can play around with that if you'd like, but you're going to end up with the same result. So in summary, when we do not know the population standard deviation, we should use this confidence interval. When we do not know the population standard deviation, if, this is the big one, if, I'm going to put 2 f's, if and only if, n is greater than 30. So if we have a large sample, we can use that formula to solve for the confidence interval. And if the sample is small, we are going to use a different formula. We've already seen it. It's just based on the t So if we don't have the population standard deviation, we use this if we've got a large sample, or we use the yellow if we've got a small sample. All right, moving on to hypothesis testing. So moving right along to hypothesis testing. Hypothesis testing. So we can conduct hypothesis tests using the confidence interval approach, and we've already discussed that, but we can also use a null and alternative hypothesis. So sometimes we wish to test the null hypothesis, that mu is equal to some value against the alternative hypothesis that the true value does not equal some value. So mu is the population mean, and we estimate with y bar. So we can think of c as some temporarily assumed value for mu, and we can compare a sample statistic to this sort of temporarily assumed value to see if we have strong sample evidence that the true value is something different than the hypothesized value, in this case c. So if our sample statistic has a normal distribution, and it does, so here we're talking about the distribution of the mean. So if our sample statistic has a normal distribution, we can temporarily assume that the true value is c, that the true value is equal to c, and then we can compare. So we're saying that that mu is equal to c, that the true value is equal to c. I can grab a sample, solve for the sample statistic, and then I compare the sample statistic to the true value. And of course, if my sample statistic is very, very large relative to c, then that's evidence against the null hypothesis. So I might reject the null hypothesis and make the assertion that mu is different than c. So again, this is just hypothesis testing. When we see examples, it'll make a heck of a lot more sense. Also remember, y bar and s are the mean and standard deviation of a sample of size n that has been randomly selected from the population having mean mu, and the t-value is simply equal to, in the context of hypothesis testing, y bar minus c divided by the standard deviation divided by root n. So if our sample statistic has a normal distribution, we can see how far our sample statistic is from the hypothesized value. We can basically compare y bar. If we get a y bar that's way out here, we can basically say, you know what, that's different than the hypothesized value. But we perform this comparison using the t-score. So we normalize our sample statistic. In this case, the normalized mean is 0. And if we get a t-value, or a normalized sample statistic, that basically we temporarily assume that c is equal to mu. So if c is equal to mu, and I get a value much larger than c, this numerator is going to be very, very large. And remember, if that difference divided by s over root n is something like 4 or 5 or 6, basically what we're saying is that the observed value is 6 standard deviations from this temporarily assumed value. So if we assume that the true value, mu, is equal to c, but we see a sample statistic that is much, much larger than c, we might reject this null hypothesis. On the other hand, if the sample value is very, very close to c, we might not, and then once we, when I say very close, what specifically do I mean? When I say y bar is very far from c, what specifically do I mean? I mean close and far in terms of standard deviations. Now we're talking about a sampling distribution, so standard errors. So if we are 3 or 4 or 5 standard errors away from the hypothesized value, this temporarily assumed value, we might reject that hypothesis. But if we are very, very close, maybe 1/2 standard, like if we're very, very close to the hypothesized value, we will fail to reject the null hypothesis. You know, one of the things that we learned is that the sample mean is an unbiased estimator of the population mean. So even though the sample mean does not equal the population mean, the average of all the different sample means that we could have calculated is equal to the true population mean. Also, if the population is normally distributed, then we know that the sampling distribution of the mean is normally distributed. And once we know the sampling distribution of the mean, we can make those probability statements about sampled values versus hypothesized values. So again, if the sampled value is close to the hypothesized value, in other words, if we get a small t, then we're not going to reject the null hypothesis. But if we get a sample value that's far from the hypothesized value in terms of the number of standard errors from the hypothesized value, we might reject the null hypothesis. In that case, we have statistical evidence that the population mean is very different than the hypothesized value. So you guys have been through sampling, you guys have been through hypothesis testing before while working on your, while working through your first statistics class, but this is a nice review. So when we see some examples, this will make more sense, but again, if the t statistic, we're going to be solving for this t, and if this t-stat is very large, this provides evidence to support rejecting the null hypothesis. Basically, what's going to happen is that the firm is likely going to have to intervene in some way, shape, or form. All right, let's review what a type 1 error is and a type 2 error, and then we'll sort of move on to examples. A type 1 error is committed when we reject the null hypothesis when it is in fact true. So if we assume that the null hypothesis, or if we temporarily assume that mu is equal to c, and we get a sample value that is very large, let's say we get a sample value past the critical value, which includes 2.5% in each tail, that's going to happen 5% of the time by chance. So just because we get a very large sample statistic relative to the hypothesized value doesn't necessarily mean with 100% certainty that mu does not equal c. In other words, we don't accept the alternative, we just reject the null. In other words, we've got evidence that says that mu does not equal c. We're not saying that mu does equal c. And if we specify the level of confidence to be 5% or the level of statistical significance, if we specify alpha to be 5%, or we put 2.5% in each tail, so the level of statistical significance is 5%, then we are going to randomly get values, sample statistics, that are greater than the temporarily assumed value, the hypothesized value, 5% of the time. So even if the null hypothesis is true, we're going to reject it 5% of the time. So that's really important to understand. So very quickly, if the population is normally distributed, and we know that it is with mean mu, we can reject the null hypothesis that mu is equal to c in favor of the alternative hypothesis that mu does not equal c by setting the probability of a type 1 error equal to alpha. So here is what alpha, so that's what alpha is. It's the level of statistical significance, and it's equal to the probability of committing a type 1 error. And again, this is something that we choose. We might feel comfortable with an alpha equal to 0.5. In other words, if we're wrong 5% of the time in the social sciences, we can live with that. So if we solve for t and we see that t is greater than the critical t value that includes alpha divided by 2 in the upper tail, 2.5%, or if we see a t that is less than the critical value, so less than the critical t value, that puts 2.5% in the left tail. If we observe a t greater than the critical t or less than the critical t, we can reject the null hypothesis. Again, the level of significance tells us that when we reject the null hypothesis, we're still wrong 5% of the time. So if we want to be wrong only 1% of the time, we need to change alpha to 0.01 or 1%. A type 2 error is committed if we do not reject the null when it is false. So if we fail to reject a false null, we commit a type 2 error. There are different things that we can do to control the probability of a type 2 error. That's a little bit advanced. We won't get into that. But we can choose the level of statistical significance, and we can pick the probability of a type 1 error. Typically, in the social sciences, alpha is equal to 0.05 or 0.01. Sometimes for certain problems, we might set alpha equal to 0.1. All right, so recall that if the population sampled is normally distributed with mean mu, then the population of all possible values of y bar minus mu, but divided by the sample standard deviation divided by the square root of n. So if we replace that sigma with an s, so y bar minus mu divided by s divided by root n, these values, or t values, follow a t distribution with n minus 1 degrees of freedom. So it follows that if the null hypothesis is true, then the population of all possible values of the test statistic t is equal to y bar minus c, our temporarily assumed value of mu, has a t distribution with n minus 1 degrees of freedom. So again, we can find those critical t's and compare the calculated t's to the critical t's to determine whether we should accept or reject a null hypothesis. So these are the steps to hypothesis testing. Actually, I probably should have just started with going over the steps. So the steps to hypothesis testing are, first, you state in advance the level of significance. You have to pick that in advance. You state in advance the decision rule, or the null and alternative hypotheses. You compute your test statistic. Then you compare the test stat to the critical stat, and then you use that information to determine whether or not to reject or fail to reject the null. We don't accept it. We either reject it or we fail to reject it. All right, so let's do an example, and we're going to assume a significance level of 0.05. So let's say this corporation takes a random sample of n is equal to 6 bottle fills. So these are bottle fills. So again, when we do examples, it just makes a heck of a lot more sense. So we're taking 6 bottles. We're taking a random sample of 6 bottle fills from its bottle filling process. So we're thinking about some sort of a business process improvement example. And we want to state the null hypothesis that mu is equal to 16 ounces. And the alternative hypothesis is that mu does not equal 16 ounces. So why would we state this sort of hypothesis? So let's say that we get a sample comprised of 6 bottle fills, 15.68, 16, 15.61. Let's say that we get a sample comprised of these values. So I'm going to clear the data and I'm going to input this fills variable. I'm going to list, and these are our 6 sample values: 15.72, 15.86, 15.93, 15.61, 16, and 15.68. So we take this random sample, and this is what we get. What do we do next? Well, from this sample, we can solve for the average. Let me do that very quickly. So I'm just going to put SU for summarize, and we see that the average is 15.8. Now, what are we hypothesizing? That's a little low. This is a bottle filling process. We want to make sure that our customers get 16 ounces. If we're getting 15.8 with this standard deviation, do we have a problem? So let's see. We have to solve for the critical t-value. We know that if I standardize this number, this 16, it follows the t-distribution, so we can compare the calculated value to the hypothesized value. We know that the standardized mean is equal to 0. So if we temporarily assume that the true mean is 16, then 16 minus this temporarily assumed true value divided by the standard error, whatever it is, s divided by root, if we assume that the temporarily assumed value is equal to the hypothesized value, we get a 0 for the mean, and we can compare the critical value to the critical t-value to the calculated t-value, or the normalized value for bottle fills. That's what the calculated t-value is. So we're going to put 2.5% in the left tail, and we're going to put 2.5% in the right tail. We know that n is equal to 6. So if n is equal to 6, what is the critical t-value? Well, let me open up my t-table and we'll check it out. So I've got stat tables here, and this is my t-value table. This is my t-table, and we've got a sample of 6. So if I go to degrees of freedom equal to 5, and we're going to let 2.5% exist in the upper tail, the critical value is 2.571. So the critical value, T critical, is 2.571, and since it's symmetric, it'll be negative 2.571. But the negative amount isn't really meaningful, so normally we would conduct a one-tailed test in this case, and we can do that in just a second. But we have to compare the critical value to the calculated value, and remember the calculated value is, or actually this negative will come into place now that I think of it, because we got a sample mean less than the hypothesized value. So basically what we need to do is standardize our sample mean. So if I go to Stata, I see the sample mean is 15.8. So remember, the t-value is equal to the sample mean minus the hypothesized value, all divided by s divided by root n. And we saw that the standard deviation is 0.1532. We know that n is equal to 6. We know that y bar is equal to 15.8. That's going to be 15.8, and we know that we are assuming 16. So let's solve for this t. So the t is 15.8. And again, basically what we're doing is subtracting out the temporarily assumed hypothesized mean and dividing by the standard error. So we're going to see how many standard errors our sample statistic is from this temporarily assumed value. So in other words, we're just going to solve for a standardized measure of bottle fills. or this particular sample of bottle fill. So 15.8 minus 16 divided by 0.1532 divided by the root 6. If you solve for this, you will get negative 3.2. Now, since the absolute value of this is greater than the critical t-value, or since negative 3.2 is less than negative 2.571, in other words, the calculated value is less than the critical value, we won't observe this if the true hypothesized value, or if the hypothesized value is true. In other words, if it's really 16, once I standardize it, very rarely will I observe a sample value that is 3.2 standard deviations from the hypothesized value. I'll observe that less than 5% of the time if the cumulative area in both tails is 2.5%. So the p-value is the probability that I observe a sample stat at least as large as that observed given the null hypothesis is true, and we know that's less than 5%. Basically what we're saying is that following the steps, the rule says that if this is less than the negative 3.2, the calculated t-value is less than the critical t-value, we reject. We reject the null hypothesis. So how do we do this in Stata? Well, I love it in Stata. You just put t-test fills is equal to, and then you put the hypothesized value, and you see that the t-value is negative 3.2 about, and everything that we got, Stata gives automatically. So if I do this in Stata, it's really that easy. That is all that we really need to do for the statistics review. I'm going to go ahead and go through the rest of the notes, but as far as the Stata program is concerned, I can put exit here, and I will have completed nearly everything in the notes. If I run the entire program, Stata is running. We've worked with some pretty big data, so that's why it's taking a while. And remember, we wrote this do file so that a log was created equal to statreview.log. So if I view statreview.log, I get everything that was produced by my program. So we get all that wonderful stuff. All right, so moving right along, we can also do a one-tailed hypothesis test. Again, it's the same process. The only difference is how you write the null and alternative hypothesis. And this is something that we are going to do in class quite a bit. But we might write the null hypothesis if it's a one-tailed test. In other words, if we have reason to believe that the true value is greater than some hypothesized value, put what you believe is the case in the alternative hypothesis. So we might say that mu is greater than 30. The equal sign always shows up in the null, and I could put mu is equal to 30 there, but since I'm using greater than in the alternative hypothesis, I'm going to put less than or equal to 30. And basically what we're doing is we're taking all of the area under the t distribution. Instead of dividing it between two tails, I'm going to put that full 5%, the full 5% in one tail. If that's the case, like in our previous example, if we had degrees of freedom equal to 5, but we put all 5% in the upper tail, the critical value goes to 2.015. That makes sense, right? If I take this percent and put it in here, in other words, I'm taking some of the percent from this side and I'm putting it all on this side, then I'm going to move to the left a little bit, and my critical value is going to move to the left. And instead of 2.571, we're going to get, I forgot what it was, but with 5 degrees of freedom, 2.015. 2.015. So that would be 2.015. So I put 2.015 there. That's my critical T. So that's the T alpha, not alpha divided by 2 because it's in one tail. I still got my degrees of freedom. That's the critical. And then I solve for the sample statistic. Let's say I get a sample statistic equal to 2.132. Well, it's greater than the critical value. I reject the null. I have statistical evidence that it's greater than 30. So how do we do this in Stata? It's really easy. We'll use the miles per gallon data. I'm going to summarize miles per gallon. I see that the mean is 31.2. I'm going to temporarily assume that the mean is equal to 30. So I'm going to put t-test miles per gallon is equal to 30. Boom. I solve for the calculated T. Oh, my bad. In this data set, we have 4 degrees of freedom. So the calculated value is 3.56. The critical value with 4 degrees of freedom and 5% in one tail is 2.132. So this, in the example in the notes, is 2.132. And then the calculated value, so that's the critical value is 2.132. The calculated value is 3.569. And since that calculated value is greater than that critical value of 2.132, again, we reject the null hypothesis. I know it's super easy. You can also include in the alternative hypothesis that the mu, the true value, is less than some hypothesized value. Again, this is something that you can do in Stata fairly easily. We're going to use Phil's clear list. And I'm going to summarize Phil's, and it's 15.8. Oh, I'm sorry. I'm looking at the p-value. The last example in the notes explains the p-value. So example 7 is just another example. I don't think the data is in Stata. So you can just read through example 7, but we're just basically saying that the alternative hypothesis is mu is less than something, 60 in this case. And again, if we are including in the alternative that mu is less than something, in the null it's going to be greater than or equal to. The equal sign always shows up in the null. And we're going to compare the calculated value to the sample value. The calculated value is greater than the sample value. I'm sorry, if the calculated value is a larger negative number than the critical value, we're going to reject the null, and that's the case. And then the p-value, we already said that the p-value is the probability that you observe a sample statistic as large as that observed, given the null is true. And the p-value is given to us in Stata. So this is the null in our previous example, that the mean is greater than 30. The probability that we see a value greater than the hypothesized value given the null is true is less than 2%. So in our Phil's example, we did the t-test that Phil's was equal to 16. The mean was equal to 16. And here we get a p-value that, again, that is less than the critical value. So if the p-value is less than the critical value, and this is what we're looking at here, but if the p-value is less than the critical value, then what we are going to do is reject the null hypothesis. The p-value is just the probability that we would see a sample mean equal to 15.8 if the true value is 16. So if the probability that we see a sample value this small, if the null is true, is only 2.41%. In other words, this is so rare, the sample statistic is so rare, we only get a 2.41% by chance. And that's too low. We're going to reject the null that the mean is equal to 16. There's something wrong. The firm is going to have to intervene. We're going to have to change the specifications on the machine and make sure that the ounces increases a little bit. We want to fill up these bottles a little bit more so that we don't have mad customers. All right, so that is the stats review. I probably should have done this in multiple sittings, but you can always, pause it come back to it, review the notes as you see fit. You may or may not need to do the stats review, but if you do, it's been recorded. I hope this helps. If you have any questions, please feel free to reach out. All right, have a good one.